right, so next up we have a panel discussion. It's going to be led by David Shaw, Chief Analyst at Global Quantum Intelligence.
So let me kick off by asking each of the panelists just to very briefly introduce themselves, but only briefly because we're going to come back in a bit more detail later on. Andrew.
I'm Andrew Dzurak. I'm the CEO and founder of Diraq. Been in the field of quantum computing for about a quarter of a century. Launched the company 2 years ago.
Shmuel.
My name is Shmuel Bachinsky. I'm CEO and co-founder of Quantum Transistors. We're a 2-year-old company, a second-generation quantum hardware company.
And I'm Smets. I'm the CEO of Quantum Circuits. I've been involved with quantum circuits for about 1.5 years, so I am truly a newcomer. So it's really good to be here.
So I wanted to first of all set the scene about why do we need, this is the new faces panel, why do we need new faces, even if some of the faces that are new have been around for quite a while. Why do we need new faces? Because we've been hearing all these great presentations at this conference about this first generation qubit architectures and how well they're doing and all the progress. So let's set the scene by challenging some of that narrative. You know, Andrew, in conventional computing, we talk about Moore's law. Moore's law has conditioned us to think that smaller is better and everything gets smaller over time. So why is that not going to be the case for first generation quantum platforms? What do we expect the challenges to be there?
Well, I mean, as people are aware, there's a number of different technology platforms being pursued at the moment, probably 5 or 6 main technologies. And most of those have physical limitations on the size of the qubits, be it superconducting, be it photonic, etc. And many of them really can't operate down at the smaller size scale. So unlike in the case of classical Moore's law, which was essentially set by the manufacturing limits. I mean, transistors could keep working as you got smaller and smaller. In general, this isn't the case for quantum bits. And so really the challenge is, can you find quantum bits that are small enough to get enough into a compact area?
Mm-hmm. Shmuel, I wanted to come to you about another aspect of this, which is, we've heard a lot about the chips that have been launched by the different first-generation manufacturers, and that's great. But often these systems aren't really about one chip or just one fabrication technology. What are the different chiplet challenges that we have to solve, and why at different layers, and why does material choice matter?
Well, first I'd like to refer to the general question is why do we need new faces? I'm old enough to remember the Motorola brick phone. And the iPhone in my pocket right now is almost unrecognizable from there. So any technology that the first generation is successful commercially is basically a reason to keep going, right? To make it better, to make it smaller, to make it faster, to make it cheaper. So that's why, obviously, there will be a second generation if the first generation is successful. And I have to say, after this conference, I'm much encouraged about the success of the first generation. I'm counting on it. Now, for us, well, before I say that, we're building a single-chip quantum processor, okay? And basically, we call it the 8086 of the quantum world. And to do that today required us not just to make material choices, but use multiple technologies. So for us, as I'll show later maybe, the chip is composed from diamond qubits, from silicon photonics, and from silicon ASICs. So there's 3 layers, 3 different technologies that all have to come together in a single package to make that technology happen. The challenges are obviously there. If I could do the whole thing on a single material, like maybe Andre is trying to do on silicon, I'd be very happy. Maybe it works, maybe mine works, we'll see.
Right, I mean, with that in mind, of what it's going to take to offer breakthrough qubit performance, what is the real lead metric there that we should look out for, but what's going to give us that performance?
It's a great question. So clearly we want really great 2-qubit gate fidelity numbers. And you want to have the ability to detect and eventually correct errors. So the approach that we're taking is, I'm very fortunate to work with a group of people who invented the transmon. But that was just the beginning of a long arc of innovation to bring something new to the table that actually could do something better. We need innovation. We need to do things differently. Sometimes it's bigger, sometimes it's smaller. But at the end of the day, it has to be more effective. It has to do something else. So the objective for us is really to deliver a new kind of qubit, which we just birthed into the marketplace. It's just entered into this domain. that brings the best of kind of the great work that's been done with the trapped ions and neutral atom side with great fidelity, with the benefits of superconducting, so you have fast clock speed and scalability, and you bring that combination of capabilities together in a validated qubit approach that has the potential to scale. But it's got to work, and it's got to work with a lot smaller footprint in order to be practical. So I think there's a couple of different metrics there that are important, but it's got to perform, it's got to scale, and it's got to be practical.
Now, there's another topic that we've heard a lot about at this conference, which is error correction. And it's a very hot topic, and it's quite a difficult topic as well, it seems to me. So I wanted to explore some of the themes there. Now, Andrew, the surface code, why has that been such an influential code in the development of the sector? But also, do you think it's going to be the way we get this done, or are we going to have to look for a generational change in error correction technology?
Well, the surface code has been so popular, firstly because it's so tolerant to errors. It was a breakthrough at the time because it showed that with error rates of, as bad as 1%, which is, 99% fidelity, but, still relatively reasonable threshold to target, that one could build fault tolerance. And we've seen exciting results this week from Google where they've started to demonstrate really impressive demonstrations of up to 100 physical qubits, pushing down logical error rates with the surface code. One of the reasons it remains such a popular paradigm is because it's probably one of the best studied and understood. My view is that ultimately we will end up with modified error correction codes. There are many variants of the surface code. For example, our company is looking at variants of the surface code that can be done in more relaxed architectures than the strict 2D arrangement. So I think ultimately there will be variations, and some of these codes are actually designed for particular types of error profiles for different types of qubits.
Actually, I wanted to ask Ray to elaborate on that, because I know it's a subject close to his heart. In trying to tame these overheads, we've often talked about threshold and 2-qubit fidelities, but there is more subtlety to that overall error model. And maybe you could talk to us about some of the other games we can play to.
Yeah, so this is really what it's the foundation of quantum circuits. The ability to remove the error in creative ways while still maintaining the fidelity that you need in order to scale. What we have is something called a dual rail qubit. It's multiple transmons combined with a couple of cavities. And the way that we manage that and develop that solution, it's quite innovative. We have a 3D model of it in our booth. Please come check it out. It actually delivers kind of a bridge towards an error-corrected solution. Our approach is basically to begin to learn where the errors occur. And so we're doing error detection with our dual rail qubit. So we, just like every other qubit, we deliver the data. It's a 1 or a 0, depending on the circumstance with the photon. But we have a novel approach to the solution by delivering a third piece of information, and that's whether or not an error occurred. If you look at the error hierarchy, we have to deal with errors just like everybody else. We all have to deal with them. But the design of our solution allows us to convert a lot of the errors into something we call the erasure. And that erasure happens to be very easy to remove. So we can remove about 90% of the errors before we get to surface code, and we will get to that as well. We still have about 10% errors to remove, but this bridges the gap very significantly to the ultimate goal of eliminating the errors with both error detection and error correction combined. So so absolutely that's the trick. The trick is a new kind of qubit that actually knows its own error, knows when it occurs, knows how it occurred, and it actually reveals that to the algorithm developer so they can take action in the algorithm to mitigate it.
Shmuel, now another thing that we've heard a lot about at the conference is people looking at enhancing qubit connectivity, both on chips and between chips. And why is that so important here?
Well, I guess it ties into the other questions you just asked, because being a second-generation company means that when you get to market, you expect the value chain to be much more mature. Already today, we see companies that are specializing in error correction and error detection. And if you wait 2 or 3 years, which is the time we need to develop our processor to maturity, then we don't expect to reinvent the wheel. We expect to give those companies full access to the physical level and tell them, okay, tell me, based on what I have right now, what's the best approach I can use, and also what can I do in my hardware to make your life easier. Now, so I don't have too much to do, I'm improving the flexibility of my hardware architecture right now to give them the most tools to work with when I get to them, okay? So we don't actually expect to do any of that stuff. We expect to give a physical layer that's very, very flexible and completely open it up to the people above us in the value chain.
So I thought, in that this is the new faces panel, it would also be good to have some new slides. So we're going to give each of the panelists a strict 5-minute slot for them to do their extended elevator pitch. So if I could ask for the slides, our first slide is up there. So Andrew, shall I click them through if you give me the nod, or do you want to click yourself?
I'll
Click yourself.
give it the click. Let's see. So
5 minutes, please.
No problem. So our technology is based on standard silicon integrated circuit design. Our quantum bits are, in fact, modified MOSFET transistors that make up all of the electronics that we use today. We showed around a decade ago that we could create high fidelity operation of an electron spin bound inside a modified CMOS transistor. The beauty of this is we have super high density of qubits. It means if we were going for maximal density, we could actually get billions of these silicon qubits, even on a single chip. Now, with the architectures we use, because we need to relax the interconnect density in order to get in the control and readout electronics, it means that we reduce that density somewhat by a couple of orders of magnitude, but it still allows us on a piece of silicon to go to the many, many millions, in fact, tens of millions of qubits. This allows us to get everything into one compact system. So our team had been working on this for, as I said, nearly 20 years. We demonstrated the first of these CMOS qubits 10 years ago. We launched as a company in May 2022. We now have over 40 staff. We have a subsidiary in Europe based in Germany, and we've just set up a subsidiary here in the United States, Diraq Incorporated. We will have an office opening in Silicon Valley in the first quarter of next year. Two of our senior team, Andre Sariva and Analyst, are already here today, but Anna on the East Coast in Boston already, Andre heading out to the West Coast. So we're building up a team here, both mainly the design area. So if I go to my next slide, the core aspect of this technology is the ability to integrate so many qubits into a single cryogenic system. We're looking at tens of millions of qubits in a single refrigerator. This means that we can get the cost of a fault-tolerant quantum computer down in the millions of dollars rather than in the hundreds of millions of dollars or the billions of dollars that alternate technologies are looking at. So this is really what we're talking about, the next generation, getting the cost down and making it affordable. We see ultimately for quantum computing to be a ubiquitous paradigm, we need not just to have one or two of these quantum computers, we need thousands of them located in a data center so that users can access these and mix this with advanced AI and classical HPC so that quantum computing will just be a standard routine that those HPC units will call. And it's all based on CMOS technology, and our key partners here in the US are Global Foundries, and in Europe, IMEC, which is the world's largest R&D fab. In fact, with IMEC, we've recently demonstrated on the public archive the demonstration of all gate fidelities, 1 qubit, 2 qubit, initialization and readout, all above that 99% fidelity threshold, errors below 1% as required for error correction. Very confident of the ability that this will scale up to the numbers required for true fault tolerance. How did I do, David?
You did very well, very nice. It's time for me to ask you a question here.
Okay.
So one of the things I remember as learning when the superconducting circuit guys first jumped from a handful of qubits to chips with tens and then hundreds of qubits was suddenly we really realized how difficult crosstalk was as a problem and calibration of those qubits was as a problem. So should we expect the same challenge when you start scaling, or have you got
let me tell you a little bit about, I might hand it on to you, Ray.
Ray.
Actually, I think it's Ray.
Sorry, it's Ray next. Yeah, so on the issue of crosstalk, the way that we've largely engineered around this is by having a single driving microwave field that drives all of the millions of qubits. So then crosstalk actually is just limited to the fact that our adjacent silicon devices will have an electrostatic crosstalk, but it's only with nearest neighbours. That means that we can do a simple linear combination of gate voltage pulses in order to correct for it. Coming to the issue of calibration, that's also crucial. And fortunately, there's actually now a number of startups that are starting to work on calibration of both. They've been doing a lot on superconducting qubits, now doing them on these silicon qubits as well. And we're working closely with those partners to do the rapid setup of the chips.
It's a great example. I think often when people they hear, oh, it's a silicon spin qubit, and people think, oh, it's another one of that same approach, but it's these details, important details of differences in what different players are doing that may make a very big difference for you.
I'll just add that one of the great advantages of using silicon technology is that you can leverage so much of the existing industry's capabilities, be it in the packaging, being it in the design. I mean, we use Cadence to design our chips, right? Okay. That leverage of capabilities is really crucial. And we see an ecosystem building in the quantum computing world exactly as it has in the traditional semiconductor world.
Ray,
All right.
5 minutes.
5 minutes and counting. Well, we're a new face, but clearly there's a very well-known face on this slide. I love this picture. We're Quantum Circuits. We're based as a spin-out from Yale University, based in New Haven. And we have a pretty well-known guy as our founder and chief scientist. His name is Rob Schoelkopf. And if you guys, most of you guys know who Rob Schoelkopf is, a lot of you may not know who Quantum Circuits is. If you tried to Google us maybe about 6 or 8 months ago, you probably would not have found us. This year has really been a year where we've come out to tell the world what we've been working on. You know, Rob is basically his whole life, his whole career has been focused on advancing the concept of quantum computing to a practical ultimate solution. And Quantum Circuits is really the outlet where that's actually happening. We have a very clever relationship with Yale. We share about 105 patents together between us and Yale, and more coming, by the way, because there's a lot of innovation happening. We're about 70 people big, most of which are PhDs, of course, as you can imagine. And we have a really incredible syndicate of investors who believe in this technology. One of the things that we think is very important to us, in addition to having one of the most amazing people, amazing teams of engineers and quantum physicists working in the company, is the fact that we've been able to come so far for so little money. We've only raised $85 million. We've got 2 working QPUs. We've got customers using them. We have them running their algorithms through our software stack, and they're basically delivering interesting results. And we just introduced through a PR release the name of the actual QPU. It's called Ackermann Seeker, so it is called the Seeker, and we actually have a customer validation point that goes with that. But the real star of the show is Rob Schoelkopf, and Rob's approach was once he developed the solid-state transmon, it was kind of off to the races. Everybody was off to the races, and he graduated many of the scientists that work for some of the largest companies, especially in the superconducting field, out in industry today, and that's a pretty amazing accomplishment. But Rob stayed back at Yale as head of the Yale Quantum Institute, and he said, you know, we actually can innovate a better qubit, but we're going to try it in a different way. If the real predominant issue in this industry is to reduce errors and ultimately solve the problem of error correction within this industry, let's solve that first. So the approach that Rob took is to correct first, then scale. It's a more efficient approach. I'm a technology executive in Silicon Valley for many, many years. Scalability and cost efficiency is a hallmark of success in any sort of technology that you deploy within any industry, including quantum computing. So the concept here is create a new kind of qubit that is error aware, that you can actually use to reduce the number of known errors from the path to ultimate fault-tolerant quantum computing. And then, of course, you throw on top of it the surface code and error correction techniques that will get us there 100%. Don't give up any of the things that are important, like fidelity. You want to have really, really strong execution, fast clock speed, and you want to be able to run algorithms. But here's the kind of the special sauce. We bring features to the table. So everybody has a set of features, and there's some very, very good programming languages out there. but we reveal a couple of things to the industry that they've never had access to before. They now know that the error has occurred. They know which qubit it has occurred on. And the algorithm developer now has new capabilities within their programming language that allows them to do whatever they want to do within the algorithm to actually remove the error and improve the performance of the algorithm. So really, at the end of the day, we're looking at doing that, and we're also looking at a faster path to scalability. The kind of solution that we have with the qubit and the features that we're allowing for and the error detection capability gives us a shot at developing a system that is more practical. That's kind of one of the stalwart principles of this business. We agree that these systems are going to have to be large. We're going to have logical qubits. We're going to have to solve the problem with logical qubits. But we got to think about a more practical approach than football field-sized computers. If we can get this down to about 1/10 the size of those kinds of systems with the same kind of performance, we've increased the potential for success within our industry, and we're very, very happy to do that. So really just kind of to encapsulate, we've got a new kind of qubit. It sits right in the domain of the superconducting domain. It works just like all the other qubits. It delivers an additional piece of information that delivers incredible value to the algorithm developers. And we're really, really happy to see where it fits in the architecture.
Clear appeal. But I guess we're having to look at a slightly larger footprint of circuitry on chip. Are we going to have to accept a slightly slower clock speed as well from this?
No, actually not. Well, with any sort of design, you have trade-offs, and clearly the dual rail solution has a trade-off. Come take a look at it. We have a 3D model. It's pretty interesting. We're not going to give up clock speed because we're superconducting. We bring that to the table. Of course, there's a slight variation there, and there's also a slight size-related issue, but the impact and the benefit that you get from that is so monumentally larger than that it's worth the trade-off.
Shmuel, 5 minutes. The clicker is yours.
Oh, I'm not going to need 5 minutes. So if you are going to buy a computer today, and we've heard just two great talks from Boston Consulting Group, this is what you get, right? So large, 12.5 million median cost point actually sounded to me a bit low from everything else we know about. And these are mainframes. Basically, if you're old enough to remember mainframes, I learned to program on a PDP-11. This is what you get right now. And this is what we want to give you. So very similar to what Andrew mentioned before. We're talking about spin qubits. We're talking about using semiconductor technology. We've built our own fab to build those qubits in our facilities in Israel. And we're talking about combining those spin qubits, not from silicon, from diamond, with silicon photonics. So let's start with the qubits. Why diamond? Diamond has some very, very interesting physical properties at the material level that enable better qubits and better performance. I don't think anybody here in the room can dream about working in anything above 1 Kelvin. Diamond can enable us to work up to room temperature, but practically for our first generation, we're looking at 4 Kelvin plus. Okay? We're hoping for 40, but we're starting at 4. The reason is because diamond is a very good isolator of thermal noise from the environment. So each qubit doesn't have to be so cold to be effective. Why are we using silicon photonics? Very early in the process, we realized that everybody now needs to get some kind of transduction into optics to be able to connect their system. So we said, why not start at that? Every one of our qubits is connected to all the other qubits, only photonically. They don't have any reason to be next to each other. They don't have any interaction between them. Each of them is single and doesn't interact with anything else. They emit photons, and those photons get processed in a photonic system in a very similar way to a photonic quantum computer. So it's really natural qubits with very long lifetime, very high fidelity, the same thing you see in neutral atoms, but with the connectivity derived from photonic links. So it's very easy for us to put two chips next to each other, get fiber between them, and again, extend our system, because the whole system is built photonically from the beginning. So this combination of natural qubits and the photonic connection, and enabling a higher temperature so we can get CMOS into the same package and control those qubits, basically gives us the ability, we hope, to present a single chip quantum processor at the scale that people don't expect right now. our first generation technology is probably going to be able to put 10,000 physical qubits on a 20 millimeter by 20 millimeter chip. So, well, within 3 or 4 years, this should still be very interesting. Now, you've mentioned the whole idea about Moore's law. I think up to every one of us would like to see that once they finish their first generation technology, there's a way to improve it going forward, because this is not just a one-shot race, right? It's a 30, 40 years race looking forward. So for us, the scalability today is actually not a function of the quantum layer at all. It's a function of the silicon photonics. And silicon photonics is a very mature technology with grade 1 FUPs. And as long as we can keep pushing the silicon photonics limits, we can put more and more and more qubits into the same area. Of course, there are limitations. But to get our funding, and we 140 million there and 85 million there, I feel like the poor man here, because we've only raised $20 million. But before we even got any money, we've measured the performance of a single qubit in room temperature, and we got 5 nines. So 10 to the minus 5 fidelity for a single qubit operation. It's meaningless, really, because the really important one is the 2-qubit operation. Hopefully next year I can share some performance number on that. But the point is, get a lot of qubits, get them very reliable. There are going to be connectivity limits. Even though it's photonic, there's still going to be some connectivity limits. But then you can deliver the 8086 of the quantum world. That's it.
Super.
Yeah.
So one of the things that when we talk to players that have, looking at integrated photonics, one of the topics that often comes up is electro-optic materials, BTO, thin film lithium niobate, and fast switching. Do you see yourself having to add that to your stack or not?
I want to stay alive when I get back to the engineering team. So I'm just going to say one word, yes. Some things I'm not allowed to say.
Super. We can take the slides down now, thanks. So sorry, you can blank the slides. One thing I wanted to also touch on in the panel was the investment landscape. And as you've all raised significant sums of money recently, and congratulations. Ray, we often talk Silicon Valley, famously its connection with venture capital as well. How important has it been to you being in the Bay Area, do you think?
Yeah, well, remember HQ is right out of Yale in New Haven, Connecticut. I happen to be based here in Silicon Valley. I'm spending a whole lot of time on the East Coast. It's a little warmer here than it is over there. But, think about it. Silicon Valley is the cradle of innovation, no doubt about it. A lot of the companies here have resources here that are just incredible, and it's amazing to see the innovation that's happening across the industry. But this is a worldwide phenomenon. So I think in order to be a successful quantum computing initiative, you have to be connected globally. You have to be connected globally academically, and you have to be connected globally from a business perspective. You can't look away. We're in a race to success, but we're doing this together as an industry, and there are going to be multiple winners. There's plenty of room here for many companies to succeed. So I think one of the benefits I have about being here in Silicon Valley is, yes, you're a short drive from Sand Hill Road. There's a lot of money over there that's being looked at to invest in this area because guess what? They believe in it. They know that the next significant wave after AI is quantum, and we're all very fortunate to be part of that. And there's going to be more and more and more investment in this space to make this successful. So we're going to create a giant industry. There's going to be a lot of money that's coming out of Silicon Valley, of course, other places around the world. But this is a global event. But you can't look away from Silicon Valley. There's some amazing innovation that's happening right here. So I'm really pleased to be here with a foot also in New Haven right next to Yale.
So Shmuel, you have a long background in venture. How would you assess the health of the quantum venture segment? Are companies getting the right access to capital at the moment?
We haven't been really raising money in the past year because we're okay. But I've noticed two things just by keeping in touch with the market. One is that people are getting more selective into what companies they want to invest in. A Me Too story doesn't get you funding now. And probably 2 years ago, a Me Too story would have been great, because they never knew which modality is going to have which winner, et cetera. It helps that we have a very, should I say, bold vision? Or bold is probably a good word. And beyond that fact, I think we try to be, we come from Israel, we try to be leaner and meaner. So, and I think necessity is many times the mother of invention. So if you throw too much money at a problem, you get lazy people. And so far we've been lucky to get enough funding as we needed it, but you know, 85 million sure sounds nice.
Yeah, Andrew, getting that finance, it often comes with roadmaps and milestones. What milestones do you believe second generation architectures need to have and deliver on to be competitive?
Yeah, I think that it's important to get a system out there that is targeting genuine quantum advantage. I mean, genuine commercial quantum advantage. So I in no way want to talk down what's happened with the first generation of quantum computing. I think that the work that's been done by all of the companies out there that have started to build the community, had early end users beginning to learn about quantum computing has been vital. But I mean, let's be real. All of it could be done on classical HPC, right? There's nothing at the moment that is of commercial value that can currently be done on a quantum computer. That's simply a fact. We feel that it's necessary to have something that can go that extra mile. So our companies, we're very much focused on the final end game, which is fault tolerance, but we also think it's necessary to get something out there earlier. So we're targeting our first product release in late 2028 that will be at the tens of thousands of physical qubits with a sufficient number of logical qubits to actually demonstrate genuine quantum advantage. So we made the decision, rather than, let's say, releasing what we would, for us, what we consider toy systems, we want to go for something that is genuinely commercially valuable with our first product. And now, that does mean it's a long lead without that revenue stream. And that creates its own challenges. But our view is that it needs to be real and it actually needs to be commercially valuable.
I'd like to say something and comment about what Andrew said. We all of us, rely on the first generation companies to be successful. Because we're all going to be there at the end of 28 or 29. And if they're not successful in proving commercial value, who are we going to sell to?
Of course, absolutely.
I'm going to go ahead and throw my hat into that ring too. Very, very wise choice of words there. We're standing on the shoulders of everybody that was in Generation 1. There's no doubt about it. But I think the real challenge here is, when do we demonstrate commercial value? And there's multiple things we can call it on the way to fault tolerance. That's ultimately the goal for everybody. But we do need to find a way in this industry to begin to deliver value sooner than later. So some of the experiences that we've had with error detection and revealing that into the algorithm has really resulted in some very stunning results. The algorithm developers, many of which are not here, unfortunately. We want to see more enterprises, we want to see more algorithm developers here, and we want to talk to them. Because we don't want to write papers, we want to write algorithms. We want to write algorithms that actually deliver value. But algorithm developers are getting really smart. They're trying to come up with error mitigation techniques so that they can get value even out of noisy systems. But you combine that with an error detected technique, and suddenly you've got a new level of capability that the algorithm developers actually like. So they believe they are one step closer to having commercial value, delivering meaningful results with real algorithms that deliver real meaningful results, even in the NISQ Plus arena. But we, of course, need to get them to fault tolerance. And we really need to do it sooner than later.
Questions from the audience? Who has a difficult one, preferably?
Oh, not so difficult.
Go ahead and raise your hand if you have a question. I'll run a mic over to you.
No questions. Right, well, let me dive in. Oh, we've got a question. Ah, sorry.
All right, come in.
It's difficult to see. It is difficult to see.
We heard this morning's Scott Aronson talking about his mood and maybe the lack of real problems that could be solved by quantum computing, regardless of the availability of quantum computers, simply because the algorithms wouldn't identify problems that could be solved better on a quantum computer. Do you have any views on that?
Anyone like to weigh in on that?
Well, I mean, I'll just say, you know, our objective this year in terms of bringing what we brought to the market this year was really a series of milestones. And one of the milestones that we wanted to achieve was customer validation. So we had to go find those algorithm developers and say, okay, well, here you go. Here's a new QPU, and here's a new set of features that you have to go with it. Our experience is that the enterprises and the companies that are building algorithms are making investments now because you don't want to miss this one. If you miss the internet, or you miss the cloud, or you missed AI, you paid the price. So companies may be trickling a little bit of money into this direction, but from what I can tell, there's certain verticals that are absolutely committed to finding ways to exploit quantum computing, and they're not telling us what they're doing. They're running it on our platform, but they're not telling us exactly what they're doing. But when we see the results and we see they're satisfied with the results, we know that they're making progress in the right direction. So I'm not sure I can answer that question fully, but I have confidence that there's a community of scientists out there that have some tricks up their sleeves, and they are going to be looking at building algorithms that do solve real-world problems with quantum.
I'd just add that I don't think there's any doubt that with true fault tolerance that there are plenty of problems that are very valuable. I mean, if you can accurately calculate the ground states of molecules, then when you combine that with AI, that allows you to rapidly trial different molecules, and that could be useful for catalysis, or it could be useful for pharma design. And I mean, I think that's a known algorithm. Now, that's requiring true fault tolerance to be able to enable that. That's what our company's focused on. But I also believe that exactly the sort of stuff that Ray was just talking about, and the work that's being done on a variety of different platforms at the moment, means that there will be new algorithms discovered along the way that can potentially utilize smaller scale systems, maybe with much fewer number of logical qubits than the ultimate universal quantum computer.
I mean, if I may just add my own take on that, I was really encouraged by what Scott said, because one of the fundamental thing is, do we believe that BQP is bigger than BPP? And you know, Scott said that's what we started believing, and effectively in a series of those examples he gave us, Yamakawa-Zandri, DQI, it's new reasons to continue believing that. So we have another question.
I'd like to offer something on that question, if you don't mind.
Oh, yeah, sure.
You know, when you had mainframes, the software you had was for mainframes. So you had insurance software, you had banking software, because those are the people who could afford to buy the computers, right? You didn't have any gaming, because nobody would buy a mainframe for gaming, right? But when you had PCs, all of a sudden the software market exploded, because a lot more people had access to the hardware, a lot more people wrote software. And then you actually started to find out what you could do with it. When mobile came, again, a lot more people had access to the computers, a lot more people to the devices. The software completely changed. This will happen here as well.
We have another question. It'll have to be a quick one.
Well, it can be. Do you foresee a world in which one kind of quantum computer, it could be one of these three, will eventually dominate? Or do you see that there'll be different kinds of needs, and there'll be a need for a range of different kinds of physical implementation of quantum computing? If so, what will they be?
I'm happy to have a go. I get asked this question all the time. My view is that the differences between the different technologies are so significant that the delta in costs to effectively operate them are also very, very different, and will be ultimately very, very different. And I think that, as with the existing computing industry, it's all about driving costs down and making it economically affordable. And so my view is that, I mean, that point I think is well over a decade away before there's only one technology. But I would be very surprised if you look forward 2-3 decades that there will be more than one technology out there for fault-tolerant quantum computing, because that's going to be all about cost. That's my own personal view.
Does anyone want to weigh in?
I'll just add to that. I completely agree with the timeline, probably maybe even more, considering where we are right now in the evolution. But how many classical computing modalities there are today? There's one, right? Now there are solvers, you know, all kinds of different boxes for different very specific applications, but they're niche compared to the main market. So yes, I believe one winner takes it all. Maybe 20 years from now.
And I'll just say I agree in both cases. We're going to see phases of how the evolution of this occurs. I think once we have a fault-tolerant system, I think we're going to see a variety of solutions that will continue to evolve, and then slowly but surely they will begin to combine.
Yeah.
So I think we're on our way to a very long evolution and hopefully a very short time frame to fault-tolerant computing.
Almost out of time. One very fast final round. One sentence answers. What's the most important challenge that second generation architectures need to rise to? Andrew?
Keeping energy consumption costs down.
Being much better than first generation.
Practical scaling, smaller footprint, higher performance.
Please join me in thanking our panelists.